Hello, hello. So in the previous video, we did some testing. We wrote some tests, some integration tests for our debugger. And in this video, I want to talk about the meaty chunk of debuggers, that is registers. So debuggers can stop your program mid-execution. They can inspect variables and can step through code line by line. And they are able to do this by interacting with CPU registers. So registers are like very tiny, ultra fast storage locations very near to the CPU, and to access them is way faster than accessing a RAM. And when your program runs, all the active data that is being worked on lives in these registers. So they load the data from RAM into registers before processing it. So any calculations actually happen on registers. And in this series, since we are targeting the x86 64 architecture of CPUs, you should know how the registers work on this architecture and how they are arranged in memory. So this architecture x86 64, the 64-bit x86 architecture has more than 125 registers. And to actually create a full-fledged debugger, we need some way to interact with all 125 of these registers. And to do that, we also need to store somewhere. And since 125 is a huge number, we will create a structure that can represent all of these registers for us. We want our code to be able to read and write values to these registers. And so we need to understand where they live in terms of memory address on Linux, what they store, and how to differentiate between them. On the 64-bit x86 architecture, we have 16 actually main general purpose registers, and each 64-bit wide, meaning each register has the capacity of 64 bits. And these registers, they hold the integer values that we are calculating. They store memory addresses, pointers, and anytime you do a calculation, the calculation happens in registers. You have a value, it's stored in one register, and then you have another value, it's stored in another register. Then you add them and store them into a third register, and after that they get stored into a variable. So all temporary calculations, they happen on registers. The 64-bit x86 architecture, it's a new architecture, and to support backwards compatibility, this architecture also features sub-registers. And since I told you there are 16 main general purpose registers and they are all 64-bit in size, the sub-registers exist for each 16 of them. So each of those 16 will have sub-registers. And since the size of the main register is 64-bit, the sub-registers are 32-bit and 32-bit, and then 16-bit, and then 8-bit and 8-bit, like that. So they are the lower bit size version. So for 32-bit architecture, for 16-bit architecture, for 8-bit architecture. So if you had code that was written for 32-bit architecture that was targeting the 32-bit architecture, you can actually run it on the 64-bit architecture. Let me show you how those actually look like. So this is what the registers look like. If you have a register called RAX, and it's a 64-bit architecture, a 64-bit register, my bad. To support backwards compatibility, there exists a sub-register, a virtual register called called then there exists a sub-register, a virtual register called EAX, that is the first 32 bits of the RAX register. So if your program was a 32-bit program, it would use only the first 32 bits of this register, and that program will be targeting the EAX register instead of the RAX register. Similarly, the EAX can be divided into AX, and AX can be divided into AH and AL. So AL is the lower 8 bits of the 16 bits, and AH is the upper 8 bits of the 16 bits. That's how the registers look like. Now this 64-bit x86 architecture has actually more than 16 registers. The 16 registers are the general purpose registers, but and they only handle integer values. If you want to handle floating point values, decimal values, then you need to use floating point registers, and there are actually 49 of them. And those 49, the 49 of them are again divided into subcategories. So of those 49, there are 8 ST registers, ST0 to ST7, and they are used for floating point calculations, and they are based like they would be on a stack: ST0, ST1, ST2, ST3, like that. Then you also have 8 MMX registers, multimedia registers, so MM0 to MM7. These registers are used for image and video data, as I said, multimedia registers, so they're used for image and video data. Then we have 16 XMM0 to XMM15 registers. They're called the SSE registers, and they are just a new addition to this architecture, and they are just a more powerful version of the stack registers that are used for floating point calculations and the multimedia registers. They're just a more powerful version of those. And don't worry about remembering all this. I will put a link to all this information down in the description, or I will add it in a comment or something like that, so you can check out. And then we also have some control registers. They are the MX CSR register and the FCW FSW registers. They're used to control the more powerful, I told you, the more powerful registers. These control registers are used to control the behavior of those registers. They handle the exceptions, and they handle the rounding and stuff like that. So this in total makes up 49 registers, the 49 floating point registers. And we also have then 8 debug registers. These debug registers are very powerful. They are actually used to set debug points at the hardware level. And we do that by storing register pointers. So in the debug registers, we store the pointers to other registers. And whenever that register is accessed, the hardware knows that it's a breakpoint, and it can stop the control flow. Similarly, we can also store memory addresses in these debug registers. So whenever that memory address is accessed, the hardware knows that it's a debug point, and it can stop the control flow. And we interact with all of these registers using the ptrace command. Now the ptrace command is a very powerful command. We have ptrace. So the ptrace command takes variants. We have seen that already. Let me show you ptrace. So where see ptrace detach, ptrace whatnot. We have others as well. So these are all the variants of the ptrace command. Similarly, ptrace has other variants. One of them is get regs, which stands for get registers, and set regs, which stands for setting registers. And these variants are used to read and write the data to all the general purpose registers, only to the first 16 registers, which are the racks, RA1, RA2, sorry, RA9, RA11, RA12. I'll show you a list of all of them soon. Then we also have the peak user variant of the ptrace command, and it is used to read debug registers. And then we have the poke user variant of the ptrace command, and it is used to write data to the debug registers. Or or you can also use the poke user variant to write data to a single general purpose registers. So the get regs and set regs is used to write data to all of the 16 altogether, and it reads the data from all of the 16 altogether. But if you want to write to a single register, then you can use the poke user variant of the ptrace command. And we'll get to more details about these commands. I'll show you how these work, like I'm showing you how the detach command works. Soon I'll show you that when we actually tinker with these commands and write the code that does it. So I told you that we will be creating a structure that represents all these registers for us, but we should also create something that can help us identify all these registers. So we will create an enum, and it will have 125 names, and that will be the names of all the registers. Okay, so let us come to source RDB, And let's create a new Rust file called, it will hold the information about all the registers. So let's call it register info. Register info. And right here, I want to create an enum that will help us differentiate between these registers. Register ID or name. ID seems better. And here I will store 125 names. So 125 registers in total. And let's derive hash derive. Oh, my bad. I'll derive debug. I'll derive clone. I'll derive copy. I'll derive partial EQ and EQ. I don't need partial odd. I don't need odd. EQ and partial EQ, fine. So right here, I'm going to copy and paste the name of all the registers because it's 125 of them. You can do that too. So these are all the registers. We have the RAX, RDX, RCX, RBX, RSI, RDI, RBP, RSP, R8, R9, R10, R11, R12, 13, 14, 15. The Then we have the RIP register. This RIP register is a very important register. The RIP register actually is an instruction pointer. It stores the pointer to the position of the command that is being currently executed. So the command that is being executed by the CPU at this current moment is stored in the RIP register. So this is how the RIP register will tell us where the code flow is actually when we come to debuggers, when we come to actually implement that control flow. So the RIP command, it helps us to know which line the code being executed is on. It stores the instruction pointer. Then we have many other registers, and we'll come to them soon enough. These are the debug registers I told you about. These are the more powerful multimedia registers. These are the old multimedia registers. These are the stack registers for stack calculation, for floating point calculation. These are the control registers. And similarly, we have a floating rip. So we'll come to these. We'll soon understand what each of these register is for. Maybe you can even Google what these registers are for. We'll come to what these registers actually do soon enough. But for now, these are all the registers, and you can actually see a list of all the registers. Let me show that to you. If you were to 64-bit x86 architecture registers. So I suppose you should be able to find a full list of all the registers somewhere here. So these are the 64-bit registers, these are the 32-bit equivalent, these are the 16-bit equivalent, these are the 8-bit equivalents. Then we have special instructions, we have the frame pointer, the stack pointer, we have other registers right here. It doesn't show them all. Maybe Microsoft, good old Microsoft. Are these all? I suppose so. Uh, I suppose so. What does it? What does it not have? Does it have E flags? So it doesn't. Let me show you what E flags is for. So E flags register, it is used for conditional branching. Uh, so actually, I even don't remember all the registers, what they are used to. I just Google them, and that's what we will be doing when we are coding along. Anyways, these are all the registers, and so I told you the ptrace command will be used to read and write data to these registers. The ptrace command is able to do that because we it knows where those exist on Linux. So if you were to look at the ptrace source code, it uses the structures that are part of the Linux code base to understand where each register exists in memory. It finds an offset. Let me show the code to you. So, uh, this is user underscore regs. We do not have it here. Where is it? Here it is, user. So as you can see, this is the Linux code base, and the ptrace command uses this struct to figure out where the registers exist. So it has the ptregs, it has user fpu regs, and this structure is actually used to understand where all the where is the memory, what is the memory address of each register. The ptrace command uses that, but we do not have that in Rust. This is C code, right? So the Linux code is written in C, and the memory layout of this structure in C would differ from the memory layout of this structure in Rust. So we need to replicate that in Rust. I need a way to replicate that memory structure in RAM in Rust. I need to find a way, and fortunately enough, the Rust people, they do give us that. I'll show that to you in a bit. But we need to recreate this structure in Rust, and I also need to recreate. See, this is it holds in itself another struct. This struct holds in itself another struct, which is this ptregs. If you see ptregs, and this ptregs has all the registers, has all the good stuff in it. So we also need a way to replicate this, but not just this. We have the floating point registers. All of that needs to be replicated in Rust, and replicated in a fashion that it will live in memory as it would in a C program. All right. So we can do that using the repr C annotation. Let me show that to you right now. Let's create these structures in Rust the same way that it will, so that the data and the memory is laid out the same way it would be in a C program, and so that we can use this structure to actually read the data in Linux from these registers. All right. And how the ptrace command does it, that is, it uses something known as offset. So if I have an array of size 8 and it's int 32 array, if the array starts at position 0, a memory address of 0, then the second element is going to be at memory address of 32, because the first element is at 0, the second would be at 32, and then the third would be at 64. So these 32 and 64, these are actually offsets. So we need to find the offset. What I mean to say is, we need to find the ptrace command actually calculates this offset for this ptregs for these registers, and it does that like it assumes that the memory is laid out in the same way as it is laid out in C, because the ptrace command under the hood is C code, and so we need a way to replicate this in Rust. So let us do that. Let me create a structure that will do that. Also, we can calculate this offset in Rust using an offset underscore off function. It's provided in the standard library of Rust. We can actually calculate this offset by ourselves, and it will be actually quite useful very soon. I'll show that to you where we are using it. We are actually calculating the offset ourselves as well, because I told you, and we need to represent all of these registers in our Rust code. So I need to calculate that offset, because I'm writing Rust code and not C code. I need to calculate that offset, and I need to tell ptrace that this will be the offset of this register. So get the data from this offset. So I will need to calculate that offset. And to calculate that offset, I need uh, the memory to be laid out like it would in C. So let me show that. I hope you understand what I mean. So let me do that. Let me create the user regs, the user struct that I showed you, the PT regs, and the floating point registers. Let me create all of those registers. The struct that a struct that represents all of those registers, and then we can use those structs to calculate offsets and whatnot. So let's create the user struct first. So I'm going to copy now a lot of code because it is going to be a lot of code, and I recommend you copy as well because it's not something that you should know by heart. All right. Linus Torvalds wrote this code. I don't need to know this code. So this is the user struct, and this annotation tells Rust compiler that the memory for this struct should be laid out the same way it is laid out in C code. That's what this does. This user struct has regs and other fields. And right now these user regs and user FP regs don't exist. So let's create those as well. Now again, I'm going to copy paste some code and I recommend you do so as well. Let me copy this. So these are all the registers. This is what I showed you just a second ago. This is what exists in the Linux source code. This struct right here, and I've replicated it in Rust. And this annotation makes sure that the memory for this struct is laid out the same way it would be laid out in C. And now this satisfies this regs and this uh, field of this user struct, but this still remains. So let us create this struct as well. Again, I'm going to copy paste some code and you can read. I have given some comments as to what each of these fields are. You can understand what they are required for. The user X stores all the general purpose registers. The user FP Reg stores all the floating point registers. Then it is the pad. So there is a concept of padding so that the memory is laid out correctly. So it is easier and faster to access. So the Linux code has something known as padding that is right here. So you can read these comments, and I have given some comments for these registers as well. Like I told, rip is the instruction pointer, and it's a these are all special registers. Orig racks. This is also a special register. This register, it holds the value of the racks register before a system call. So it is just a backup of the value of racks in orig racks. CS is a code segment selector. I don't know what that is. I asked ChatGPT. E flags, flags apparently is used for branching, and RSP is the stack pointer, and SS is the stack segments. I don't know what that is. I don't. Maybe I'll ask ChatGPT later on when we actually come to using these. Right now, all I know is that we need to replicate this structure because we need to access them. So these are all the floating point registers. So as uh, the stack is supposed to be 8 floating point registers, and each of them is 16 bytes in each. So what we can do instead is store a U32 and 32 of them because uh, 8 registers of 16 bytes each would be 128 bytes, and U32 into what's that? U32 is 8 bytes. It's how much? 4 bytes, right? So 4 into 32, that's 128. That's all of the bytes that we need for the stack. Similarly, I have that calculation right here. What idiot am I? Similarly, the XMM is 256 bytes in total, 16 registers, 16 byte each. So that's 64 into 4, that is 256 bytes. And we can store that. U32 is 4 bytes, and we are storing 64 of them. And then we add a padding that's also there in the Linux code. So I've replicated that as well. Now I told you we'll be using the offset of uh, standard library function to actually calculate where in memory these variables exist in these structures. And let's create helper functions to do that. What I'll do is I will create a function fn, let's call it gpr offset, and it's going to calculate the offset of the particular register in this structure. So these stores all the general purpose registers. So this function will be used to calculate the offset of the register in that struct. So it needs to return the offset, and that will be usize. And we can use the offset of, sorry, I'm calling it a function, it's a macro. We'll use the offset of macro. So user, it needs the struct user, and then regs. So offset of will calculate the offset of regs in the user struct. Because it is nested in the user struct, what I'll do is I will call it with the reg offset already, offset, and it will be usize, and I will add the reg offset to it. So what I'll do is I will actually call this function like so, gpr offset, and I will call it with offset off, and I will say user regs struct, comma the offset I want the offset of R10. So I'll call it like this. This will calculate the offset of R10 in the user extract, and then this function will then calculate the offset of R10 in user. Because it is nested, that's how we need to do it. Or maybe you can just pass in the field, but I don't know how to write a macro for you. Maybe you can write, if you're better at Rust than me, maybe you can write a macro to do that. I don't know how to do that. I'm very new to Rust. I don't know how to write macros. Anyways, since all of this calculation, the calculation of this offsets, I want all of this to happen at compile time. I want all of this to happen at compile time, because this is going to be constant. It's not going to change ever after a program, after our debugger has started. This is never going to change. So I want all of this to happen at compile time, and we can, to use this function at compile time, need to make it const. Similarly, I want a function to calculate the offset in the floating point registers. So const fn fpr offset, and I'll also send it reg offset comma usize, sorry, comma type usize, and it's also going to return a usize, and offset of user comma, it's going to be in I387. These are all the floating point registers. Now this field name comes from the Linux source code, reg offset, and the final list of uh, debuggers that we are going to have is the debug registers. So the debug registers, where are the debug registers? They are supposed to be in user. Where is user? Here are, these are the debug registers. It's a list of 8. So let's find the offset in that. Const fn db debug, or what did I call it before, dr debug registers offset, and it's going to be number, let's, that will be the index of the register we want in that array, and I'll calculate the offset of user comma, what are the debug registers called? They are called udebug reg, and we are going to return actually usize from here. And to this I need to add number into 8, because each register is 8 bytes, 8 bit 8 bits wide. So a byte, so number into 8, number will be the index, number into 8, offset, this will actually calculate the offset of the particular index inside that array. Now I'm going to create an enum to tell me which type of register we are dealing with. And I'm also going to create an enum to tell me what type of data is stored in that register. So I will create two enums. One of them we'll call it, the first one I'll call pub enum register type. And I'm also going to derive all this for this enum as well. So register type, and in it I'm going to have four variants: the general purpose register, the sub registers for the general purpose registers, sub GPR. Then I'm going to have the floating point registers, and then I'm going to have the debug registers. And the next thing I want is what type of data is stored in each of these registers. So register format, and the data you can store in in a register, it may be an int, so let's say unsigned integer. Then the data in a register can be a float, then it can be long double and vector. That is all the type of data that you can store in a register. So all the general purpose registers, they use the uint data type. All the advanced multimedia registers, the SSE registers, use double float. The stack registers used for floating point calculations use long double data type. And the multimedia registers that are for uh, the advanced multimedia registers, they also use the vector data type. This particular data type, the vector data type, is used for parallel processing of multimedia. So like for graphics engine and whatnot, that's what the vector data type is used for. So I need to now encapsulate all this information for a register. I need to encapsulate what its ID is, what its type is, what its format is, what its name is, all of that in a struct. So I'll create that struct and let's just call it a register. Uh, pub struct register, and I need an ID. So register ID to uniquely identify it. Then I'm also going to store a name for each register, and it's going to be a string slice, a static string slice. Then I'm going to have the size of the register. Its data type can be usize. Then I'm going to have the offset of the register where it exists in the user struct. That is also going to be a usize. Then I want the register type and I want the register format. Apart from all this, one thing I've left out is something known as the dwarf ID. So dwarf ID is going to be an I32. All right. So this number, this dwarf ID, it is assigned to each register in the system application binary interface that's called the sys ABI. So that's the ABI of the CPU, and each CPU defines its own ABI, and this number is defined in that ABI. So the dwarf ID, it's standard for the debug for the registers for debugging purposes. So all the debuggers, they rely on this dwarf ID to know that which register is what. So the dwarf, in the dwarf, it stands for something. I let me check what it is. It's debug with arbitrary record formats. All right. So it's the standard that debuggers rely on to know which register is what and what it is used for. I can show you the ABI for the X AMD64 architecture, and let's look up dwarf. So dwarf register mappings. This is the official documentation, and you can see the numbers. So these are going to be the dwarf IDs of each register. All right. So these are assigned in the ABI application binary interface, and these are used to refer to the registers by the debuggers, the actual debuggers that you use. And I told you the general purpose registers have sub registers. Those sub registers don't have dwarf IDs. Since they are part of a register, they are just a smaller chunk of the register. They use the same dwarf ID as the parent register. So the parent register is RAX and its child register is EAX. So EAX and RAX, they actually share the dwarf ID. So we are going to assign the dwarf ID -1 to all sub registers. Uh, this works because 64-bit x86 architecture is little Indian. So the first byte of the register will always be stored at the lowest address. So let me show you the diagram again that I showed you before. This right here. So this is the first byte of the register. So what I mean to say by little Indian is that this is a register. That is the lowest address. Let's say. So we can refer the EAX can use the same dwarf ID as RAX because then they are going to refer to the same memory location, and then the EX, since it is little Indian, so EX also is going to start from this lowest memory address, not the highest memory address. So we won't be reading the wrong memory address. We will be reading the right memory address if we use the parent's dwarf ID. That's what I mean to say. That is the final thing that we need to store in a register, that we need to store about a register. Now since these registers are static, they're constant, I don't want them to ever change. We know what all the registers we want, so let's create all of the register objects that we are going to ever need in this program, and let's store them all in a list. All right, and we are going to implement some functions that will help us find all those registers, to find the register that we want from that list. So now I'm going to copy paste a large list that will contain 125 objects of all the registers that we would need. So I recommend you copy paste a lot of this code and I'll explain as much as is required. All right. Now here comes a list. It's a huge list. All right. So this is a const list, a const registers list, an array of registers, and it has all 125 objects of all the registers that we want. I just given the correct ID, the name, the dwarf ID according to the ABI, the size of the register, the offset. I told you how we're going to call this function. I'm going to pass in the offset of the particular register from the correct struct into the GPR offset. That's how I'm just calling this function everywhere. So let me show you where I'm using something else, something other than GPR offset. It will be right here. It should be right here. GPR, GPR. So these are all the sub registers, DS, ES, etc. Then the original racks, GPR offset, GPR offset. These are all the 32-bit sub registers. Everything remains same. The dwarf ID for these is -1. They use the parents. They use the parents dwarf ID, not their own. These are the 2-bit versions. sorry, size is 2, so I guess 16, so 2 8 16 bit, and these are the 8-bit ones, high registers. These are the 8-bit one low registers, all of them, and these are all GPR offsets. Now finally we have the floating point registers. For this I'm using the FPR offset function. I'm using the FP user FP regs struct to calculate the offset. Like previously I was using the user regs because this register exists in this and this register exists in this, and then we pass it into the FPR offset. FPR offset calculates the offset of user FP regs struct in the user struct. So that will give me the offset of CWD in the user struct. And for size, we use the size of standard library function. The size of this register is going to be the size of U16. And similarly, all of these registers are going to be U16, the size of U16. This one is going to be the size of U64. And instead of actually using this size of, you can actually even hard code all of this. So U16 is going to be 2. You can, that will work. All right. That is if you know the sizes of each type of all of each register. U64 and MXCSR is U32 is 4. So the this I've used this format because U32 is easy to remember, that it's 32 bits, right? So U32 and then size of will be 4 bytes. And then we have the stack registers. Now I told you the stack registers are also in an array in the user struct. They are an array in this fp rex struct right here, right here. And then we are adding 0 into 16. It's the same logic we used to calculate the offset of the particular debug register, because see now we have a user struct. Inside of that we have the user fp-reg struct. Inside that I have an array, and in that array I have 8 elements, and each the first element starts from the 0th element, so from the 0th memory address. Then the first one will start from the 16th, and then the second one will start from the 32nd. So that's what we are adding right here, and that's how all of these go. Now all of this is quite repetitive. I've explained all the unique things about all of these registers. For debug registers, we simply use the dr offset function that we created earlier, and that's all of the registers that we are going to be interacting with in this program. So we have created that them all at compile time. That's what this const keyword does. All of these objects will be created at const time, and then this registers cannot be updated later on. So now we have all the registers that the objects of this register struct that we're going to interact with in future, created at compile time. Now all of these are encapsulated, all of the information about a particular register is encapsulated. The last thing remaining is helper functions to query this registers array. This register array is quite large, and instead of remembering at what index a particular register exists, I'm going to create a few functions that will help me find the particular register in this array. So what I'll do is I will impl register, and inside of that I'm going to create pub fn, and I'm going to query registers by name. So I want this to return an option of a register, and since we are implementing a register, so self, an option of self. But the object is already created, so we are returning a reference to an object of self. So, and that object was created at compile time, so its lifetime is going to be static. And this will take in a name, and the name will be a string literal. So str, and in here I'm going to registers dot iter dot iter dot, and I'm going to find the element with name equal to the name provided us. So register and r dot name equal to name, and I'm going to create another query method that will be querying by dwarf id. So by dwarf id, and it's going to take the id was I32, so id I32, and instead of id I'm going to take dwarf id, and it should be equal to id. And the other function that I'm going to use is finding by id, and I should name it dwarf id, and the id is the type register id, and instead of dwarf id, and oh my bad, we don't need to actually iterate since uh, enum variants can be easily converted to u8s and can be used as uh, indexes, because we have created all these registers in this. If you copy paste, all these registers will be in the same order as they are in the register id enum. This should be the same order as this in this array. So we can use the we can typecast the variant into the index itself and return simply that. So registers, and I will take the id and I will as use size. But it needs to return an option of registers, so a reference. And so instead of option, let's say if we pass in an id, all of those must necessarily exist. If we have a valid register id, uh, register must necessarily exist, so it's not an option. But the dwarf id may be wrong or the name may be wrong, that's why. So we have written all the helper query functions that will be required to find the particular register we want to interact with. In the next video, we'll write some code to actually interact with these registers. In this video, we just created all the register objects to encapsulate all the information about a particular register. And in the following videos, we'll be actually using them. We'll be actually using them. Anyways, that's it for this video, and I'll see you guys in the next one.